Let's quickly survey the different types of intermolecular forces. Something I want you to keep in mind as we go through this survey is that really we can trace all intermolecular forces back to Coulomb's law. The different intermolecular forces only differ in the extent of the charges and the types of the charges, whether they're permanent or only temporary. So clearly then, the charge distribution within a molecule is very important for thinking about intermolecular forces. Even molecules that are neutral overall may contain temporary or permanent distributions of electrons that are asymmetric. We represent these as dipoles or dipole moments. We saw this back in the series on VSEPR theory, that a bond between two atoms with different electronegativity, say carbon and fluorine, is associated with an asymmetric distribution of electrons. There's more partial negative charge on the fluorine and more partial positive charge on the carbon. Using VSEPR theory and molecular geometry in conjunction with this idea, we can conclude whether a molecule has an overall dipole moment or not, and that's very important for the assessment of intermolecular forces. So for example, if we drew out the tetrahedral structure of CH4 and looked at the individual CH bond dipoles, we would conclude that this molecule overall is nonpolar, since the bond dipoles are very small, first of all, and they're symmetrically distributed, so that the overall distribution is symmetric. CH3Cl, on the other hand, contains a polarized carbon-chlorine bond and lacks symmetry that would cancel out that bond dipole. So this is what we call a polar molecule. NH3 similarly has a pyramidal structure such that the NH bond dipole is not canceled by dipoles in the other direction. So this is a polar molecule as well, and acetone is yet one more example of a polar molecule. And with this Lewis structure drawn out like this, we can see that this carbon-oxygen bond dipole is very strong and reflects the overall dipole moment of the molecule in this upward direction. So as we just saw, we characterize these molecules with very asymmetric distributions of electrons as polar. They have permanent non-zero dipole moments. Molecules that have dipole moments of 0 or near 0 are called nonpolar. However, nonpolar molecules can still experience temporary dipole moments. That's an important idea to keep in mind, and one we're going to see in action here in a second. So a molecule like CH4, at a particular moment in time, may have more electrons, say, on this side of the molecule and some partial negative charge over here and partial positive charge on the other side of the molecule, just due to the fact that by chance all of the electrons might find themselves on one side of the molecule or the other. These temporary dipoles can be a source of intermolecular forces. To begin, let's look at the strongest type of intermolecular force, quote unquote, and I use quotes here because ion-ion forces, although they are technically interparticle forces, we typically think of them as bonds in their own right. They're ionic bonds, and these are much, much stronger than all of the other types of intermolecular forces. They're electrostatic in nature, they just follow Coulomb's law, and they're extremely strong even relative to covalent bonds because there are multiple, for example, positive particles around each negative particle, and these are in very close proximity and in a regular lattice. A hint that ionic bonds are very strong is that most ionic compounds are solids and they do not melt except at very, very high temperatures. Think about that. What does that mean for delta H of fusion for an ionic compound? That means it's enormously, enormously high. Very high heat of fusion, or a heat required to facilitate melting for an ionic compound. The direct origin of the extreme strength of these ionic bonds. When we replace one of those ions with molecules containing permanent dipole moments, we get ion-dipole forces. This will happen, for example, when we take an ionic compound and dissolve it in water. Water is a polar molecule, and the negative end of water's dipole can interact with a cation, while the positive end can interact with an anion. What we have are the partial charges of these dipoles interacting with the full charges of the ions. So for example, you see in the bottom left here, the negative end, the oxygen end of water's dipole interacting with the positive sodium cation. Here we have another example that uses acetone. The negative end of acetone's dipole, the oxygen, is interacting with the positive lithium cation. These types of intermolecular forces are the primary driving force for solubility, for example, of sodium chloride in water or lithium chloride in acetone. These ion-dipole forces replace the ionic bonds in the solid lithium chloride and sodium chloride. If we're looking at just a sample of a single compound that contains a permanent dipole, we get dipole-dipole forces as the dominant force. Quite simply, the negative end of one dipole aligns with the positive end of another, and we get attractive forces between these oppositely charged dipoles. The key to seeing that this is relevant within a particular compound is recognizing that the molecule has a permanent dipole moment. All molecules with permanent dipole moments will engage in dipole-dipole forces within the bulk compound. Hydrogen bonding is a special type of dipole-dipole interaction that occurs between OH, NH, and FH bonds. A lone pair on, say, oxygen interacts with the positive end of an OH bond dipole. And believe it or not, there's actually a covalent component here. The sigma star orbital associated with that OH bond, which is empty, can overlap with the filled oxygen lone pair orbital, which is why hydrogen bonds are directional. And if you look, for example, at a picture of ice at the molecular level, you'll notice a regular lattice of directional hydrogen bonds. Because of this directionality and the strong polarization of the OH bond, hydrogen bonds are typically stronger than other comparable dipole-dipole forces. Beyond thinking about permanent dipoles, we can also think about temporary or induced dipoles. If we take a mixture, for example, of a nonpolar molecule like O2 and put it in a solvent like water, so dissolving oxygen gas in water, for example, water has a permanent dipole moment, but oxygen does not. However, when an oxygen molecule comes into close contact with the water molecule, there's an induced polarization that can take place. In other words, the electrons in O2 are repelled by the negative end of water's dipole, and they get pushed to the oxygen that's farther away from the oxygen of water. The resulting partial positive charge that's left behind is attracted to the negative end of water's dipole. This dipole-induced dipole attraction is a kind of intermolecular force. It's these kinds of forces that, for example, keep nonpolar gases dissolved in polar solvents like water. However, because these induced dipoles are quite weak, dipole-induced dipole forces are weaker than permanent dipole-dipole interactions, which we just saw. On the weakest end of the spectrum are what we call London dispersion forces. London dispersion forces originate from this idea that at a particular moment in time, the distribution of electrons within a molecule might be randomly asymmetric, something like this. Even though on the average the molecule is nonpolar, at a particular moment in time, it's likely, in fact, that the distribution of electrons will not be perfectly symmetric. But this is only a temporary scenario, right? That particular dipole is instantaneous. It's only living for a very short period of time. And so this is an interaction between a temporary dipole and the resulting induced dipole in a molecule nearby. So what that temporary dipole can do is induce a dipole in a nearby molecule in the same way a permanent dipole can. We just saw that in dipole-induced dipole forces, leading to an attractive interaction between the partially negative end and the partially positive end of the temporary and induced dipoles. These so-called London dispersion forces are very weak. However, all molecules experience these forces. So for nonpolar molecules like H2, CH4, etc., London dispersion forces are actually the dominant intermolecular force, and good evidence that London dispersion forces exist is the fact that if we cool down, for example, methane, CH4, to a low enough temperature, it will eventually solidify. The things that are holding the methane molecules together at these very low temperatures in the condensed phase just are the London dispersion forces.